Let's talk about some IoT hacking today. IoT hacking is an area of security I've been getting more into recently because it's just kind of at this weird intersection of web app testing and reverse engineering. Even like hardware hacking and network testing becomes involved too in some cases, and that's just really engaging for me. So, what I want to talk about is a little bit of firmware reversing, essentially, and going into a little bit into emulation of firmware that's used on IoT devices. And when we're talking about firmware, generally what we're talking about is a compressed file that contains the bootloader, the kernel, and the file system. These are generally like bin files. Sometimes it'll be like an ex2 file that will contain like the file system, and they'll just put it like in a zip or something like that. Each implementation of IoT devices, you'll find out after a while, is unique. And oftentimes, because companies try to cut costs, there's going to be some sort of vulnerability that you can find if you dig deep enough. Whether that be like that the developers tried to create their own implementation of like a protocol or something. You'll generally are going to find something somewhere if you look for a less commonly used device. Let's put it that way. And when we're talking about the firmware and things like the file system, that's particularly what we're going to focus on is the file system. That's going to be things that could potentially contain hard-coded credentials, old libraries that are being used that may contain vulnerabilities in them, things like buffer overflows and stuff like that. And so when we're talking about that, you may wonder how you can get your hands on the firmware. Sometimes you could extract it directly from the hardware itself, whether there's like a JTAG or UART interface, but maybe we'll get into that for another video. In this case, though, we're going to be looking for the easiest way to get our hands on some firmware. Literally, we could just, type in IP camera. Just grab any old random IP camera name and Google for that plus firmware, and sometimes they'll just have the firmware downloadable for you whenever there's like some cases where you may need to manually install. We're not going to be doing any of these devices. We're going to do a specific device today, the D-Link DCS935L. And you can see here, I'm just going to download this one right here. I believe that's the oldest available version on the website. We're just gonna wget that. And again, you can see that this is a .bin file, right? And that's generally going to be what you're going to see most often when we're working with, or at least for me, that's what I've seen most often being used for firmware. If we just check the file, you can see it's just reading it as data. But if we run like strings on it, type that into less, we can see that there's actually some strings in here. These look like, things that get printed to the screen upon installation of the firmware, right? You can see LZMA, that's a compression algorithm for Linux files, essentially. And, that's all cool, but what's really interesting is when we run binwalk on this, and binwalk is basically going to be reading the bytes in the file to look for any headers, any magic bytes that can tell us if there's other files within this file. And in this case, yeah, we can see we got that compressed data here. but we also have the squashfs file system. And the squashfs, it's basically it is a compressed Linux file system that is read-only, and so that means that there's no persistence upon reboot. Whenever we boot into the system, whatever was programmed into the file system upon the time that it was made into a squashfs file system, that's what's going to be there every time that you reboot. There's like no persistence, and it basically uncompresses itself ad hoc whenever it needs to, essentially. So let's see if we can extract this from this bin file here. And we can see binwalk even tells us the point within the bytes of the bin file that the squashfs file system begins. So what we're going to do is we're going to use dd to basically carve out the squashfs file system. And we're going to use the skip argument and enter the number of bytes there so that it skips every other byte preceding this point within the file. And we're going to use the bs argument to go byte by byte throughout this file. And our out file, we'll just call that dlink dot, I don't know, squish, you can call it whatever you want. This is going to take a little bit of time. So while it does that, let's talk a little bit about emulation. What we're going to be doing is we're going to use the QEMU user static. You can just look for QEMU user static. That's going to be the package we're going to install. I believe it's called the same thing in Arch-based distributions as well. And this is just, this allows for user mode emulation. This is good if we just wanted to run like a single binary or something. And if you wanted to do full system emulation, you could look for QEMU, I believe it's ARM system, or is it QEMU system ARM? Or whatever the architecture is, whether that be MIPS, MIPSL, ARM, ARM-EB, I believe is another option. In the case of the full system emulation as well, you're going to need like QCOWs, basically disk images, and then you would essentially import the file system onto there and then chroot into it, and that's a whole different process. We may not even necessarily have to do that in this case with this specific firmware. And so we can see there's our boy right here, and we're just gonna extract the file system, that is, using unsquashfs. I'm gonna use the sudo permissions for that as well, so that it can retain the proper permissions and get the device files out as well. And you can see we now have a directory that's the squashfs root. So let's go in there, and we can see it's just a Linux file system. And first thing I would do when going through like the analysis of this, I would check to see what architecture that is. This is by running file on like a binary, and we can see that this is a 32-bit MIPS architecture that uses the most significant byte first, bit significance actually. It tells us what bit is what the bit is in a binary string, right? That's not super important, but it's pretty important. But since we've already installed the user mode, the QEMU user static user mode emulation command, basically, we'll be able to run most things, most ARM-based stuff. And we can just run BusyBox here. Did I use something wrong? Yeah, that should have been MIPS, wasn't it? QEMU MIPS static. There we go. There we go. and we just got a bunch of output from there. What's kind of interesting as well, worth noting, just to get more familiar with how IoT devices generally do things, you can see all these blue names. These are symlinks that are all going to be pointing to BusyBox. BusyBox is just a fat binary that has all the functionality of common Linux terminal commands, whether that be ls or cp, mv, make dir, stuff like that. That's just a good way to minimize the usage of disk space. But yeah, now that we have an idea of the architecture that we're working for, another thing I would look for would be hard-coded credentials. So if we look in the Etsy directory, we can see it looks like password is a hard link. To a file in mount, and if we check in mount, okay, there's no config directory, so we don't have that password file, but we do have this password default file, and I'm gonna bet that, well, that has a user, admin, but no hard-coded credentials that we can see so far. So, alright, another thing that we could look at, the init tab. The init tab tells us what binaries, what scripts get run upon initialization of the system. So, in this case, sysinit is going to run this RCS script, and that's super common for IoT devices. You're always going to see this RCS script getting run upon booting the system. So we can check that out. And this is mounting some directories, mounting a file system. And the reason why we're not going to be doing full system emulation for this video in particular is we want, with QEMU, you're going to have to specify each and every single port that you wish to forward to the host, because you're basically creating a virtual machine at that point. And instead of going through all the trouble of mapping the ports that we wish to have access to, we're just going to do user mode emulation on a Raspberry Pi, and the user mode emulation may not be able to handle as many multiple processes running at the same time as the full system emulation would, but I don't care. This should work fine. So what we're going to do now is mount the proc directory to the proc directory that is in this squashfs file system. We'll do the same with the dev directories and the sys directories. And now we should just be able to chroot into the squashfs file system. Now, for anyone who hasn't seen chrooting, change rooting, we're basically, it's almost like we've SSH'd into the device that this firmware is for, right? But we're basically tricking the operating system into thinking that the root is now in the squashfs directory, and now we can even see that it thinks that we're using a MIPS architecture, even though Raspberry Pi, I believe, is ARM v7 here. We can leave it and just, pretty cool, right? So from here, what I'm gonna do is just run that RCS script. And generally, when we're trying to emulate devices, it's not going to be just this easy where we can just run the RCS script. There's going to be a lot of things that are going to fail. There's going to be files that don't exist that need to exist in order for all the daemons and processes to properly run. It just so happens that with this device, it kind of just works on first try. And in some cases, you may even need to patch some binaries as well in order to, bypass conditional branches and stuff. Like, if this exists, then get into this conditional branch type stuff. I've had to do that before with other devices, but this one, again, in particular, we're just going for a really easy demonstration, and this just kind of just works. So from here, let's run netstat, and now we can see that port 443, 80, and even 8088 is now open. So let's check that out. And I'm assuming that it's just admin without a password, because that's what we saw in that password file. I'm assuming that that's where this application is getting the credentials. But as we can see, it works. We have the web interface. Now, obviously, we're not going to have a camera because my Raspberry Pi doesn't have a camera. I don't know how you would map to the to a camera that isn't the actual device's camera anyway. So I'm not doxing myself today. And yeah, I'm actually kind of curious what was on port 8088. Yeah, it's just the same thing. So yeah, we are now emulating the web interface of this device. And from here, we could, just do some more reverse engineering, some dynamic analysis of how this works. It's curious to me that it's using ASP files. I don't think that's actually what it is, because that's a Windows thing. A really old Windows thing, too. But yeah, that's IoT emulation. Maybe we'll get into some more stuff in another video, getting a little bit deeper into like the hardware stuff and more dynamic testing. But yeah, that's it for now.